Hi, my name is Jarl Ostensen. I'm the VP of Technology at Polystream, and today I'm going to talk a little bit about our code base, how we are approaching the use of C and C++, what we have learned over the years, what our practices are now, and hopefully it will be able to provide some tips and good ideas for you as well to take away. So with Polystream, we're developing a spectator engine for very large scale spectating in game called Phantom. And our technology is based on something called command streaming, which we have developed, which is a way of streaming graphics, 3D commands from a cloud instance without the use of a GPU. So we are actually streaming basically geometry and commands. So our code base contains an enormous amount of high performance compression technology. It contains a bespoke network protocol. It contains high frequency telemetry at very large scale, which is what we're running these things are. You need that. And it requires a lot of deep insights into Windows and how we virtualize the behavior of Windows so that you can run something, your application, your game, out of a cloud instance and have it being actually rendered on a client device, a laptop or tablet or what it might be. Now, our code base started out as largely C. This was about 4 or 5 years ago when we started the company, and it was a relatively small domain. And as we grew and as we added more people, especially from the games industry, we have moved on to C++, more modern C++. But it's been a very pragmatic journey. And one of the things about moving to a new language standard means that you need to move to new tools. And as many of you will be familiar with, changing your tool chain, upgrading Visual Studio, for example, is not something you just do. There are caveats and gotchas that come with it. Sometimes the tools behave differently. Sometimes, for example, optimizers might suddenly generate code in a different way that could actually have a negative impact. It could cause issues. So it is always a slow process and a very careful process and a deliberate process. But it is something that we always consider very carefully because we want to be able to use features, new features, where they make sense and where they are useful to us. And in this presentation, I'll talk a little bit about what those may be. The other thing as well I want to point out, which I'm sure very many of you are experienced with, is that you're often dependent on third-party tools and they might not develop or evolve as quickly as, for example, the standard, well, most certainly not as quickly as the standard, or even as the compiler tool chains that come with it. As a company, we're very keen on learning new things. We're very keen on trying out new things. We don't want to be stuck in our ways and not try to figure out new ways of doing it. There are lots of reasons for that, not just because it's interesting to learn new things, but also because as an engineer, and I think as a person in general, if you constantly question your approach and question the way of your thinking, that will make you better, quite simply. And it certainly helps us in terms of creating better code and also maintaining tech debt and making sure that we constantly retrospect and look at things, try to improve them, fix them, etc. So what we sort of converged on over the years is a C++ for C approach, and I'll talk a little bit more about what that means. But first, adoption of modern C++, obviously it's moved on 17, 20, I think there is talk about 23. Moving on to a new version of a language like that is an opportunity cost. It comes at a cost, and the cost of time, and becoming a C++ expert today is hard. I think we are very close to that point where a single person cannot become an expert on all of C++ completely. I think it is big enough for that to be very close and around the corner. So when you grow a team and when you have a team with a code base that people need to be able to dip in and out of and be able to work on a regular basis in domains and areas which might not be their areas that they have worked on recently, your code base, the approach you use, the standards you adopt need to be understandable. It needs to be not necessarily a lowest common denominator, but you need to be using things that make sense and are reasonable for the rest of the team as well. We also need the code to be fast, solid, and understandable. Again, sometimes when standards move, when new libraries are released, when new functionality is adopted, things will break. Not everything has been tested completely. Your code the way you use code, the way you write your application is your way of using it. And it might be quite different from what others have tested things against. So we trust things, we like to trust things, but we like to verify things as well. It is important to not just take it as given that a new release of a compiler or a new release of a standard library, for example, will just work. So make sure always that your assumptions still hold. Do good tests, use unit tests, whatever it might be that you need. But it is important, and it slows you down a little bit in adoption. I know the C++ community is quite aware of this, but it is important to do, and we can't afford not to do it. However, if there are new features and it really can make our code better, then we want to use them. But it has to make sense. It has to be a feature, functionality that really will make a difference to us and be worth the opportunity cost. C versus C++, as we see it, is fairly sort of straightforward in a way that you can separate it. In C++ is about programming with types, and very often this becomes the main purpose of what we do in C++. And types they have very high semantic density. They have a high degree of expression of how to use them, how they are combined, how they are moved, how they're copied. They're also very restrictive because they stay within that domain that semantics is how you use them. But with them, the compiler can work out code very efficiently in many cases, not all, but in many cases, from your intent. It can understand and it can capture things and stop you from making certain mistakes. For example, I mean, move is a great example of that. Moving the contents of an object to another object is a semantically meaningful operation, and being able to specify what that means, especially when you have resources that you would not want to destroy and recreate, is obviously useful, obviously helpful, and will obviously create better code. But it is about the types first and foremost. In C, programming is about operations on data, data-oriented design, as some of you will be familiar with the term. And the type is really just a classifier or a handle even. In fact, mostly it's just a handle, and we pass it around, and the code is there to operate on that data, sort of irrespective of the type. And it's not a way to express, as it is with types, a logical system. It is about, here's some data, now you do something with it. Now, to illustrate that point, here are three boxes. It's sort of three versions of the same thing. Functionality or semantics is the question. The class on top there is an asynchronous file writer class. So you can sort of guess what that does. And for reasons, probably because the class contains fields that the compiler is unable to generate default implementations for, we have to explicitly call out and implement the constructor, the copy constructor. In this case, we're deleting it. We're saying you can't do that. We have created a move constructor, assignment, etc. And we have to do this to explain the semantics of this type, async file writer. And then there is, of course, the function itself, write some stuff to it. Now, in reality, if we take a step back, this isn't a class. This is really functionality. This is a service which takes some inputs and operates on it. It's a very C-like beast. So a alternative implementation is a pure C implementation, which is the second box, where we have a create call, we have a write call, perhaps there's a close call. But that's really all it is, because in reality, all we want to do with this functionality is to create a file or open it and then write to it. The fact that the async file writer type has semantics for how we can move it around and what we can do with it in our code is actually not important to this particular problem. We can then take it a bit further. We can say, well, actually, let's make it a C++ version of the C interface. So we use a namespace. In this case, we've changed it a little bit, added some functionality, but it's the same general idea. This is a service. This is a piece of functionality that does something, and there is no real need for us to worry about the type. And this is sort of the essence of, in many ways, I think the essence of the presentation, and what I'm trying to get across as well is that perhaps obvious to many of you, but it is an easy mistake to make. We fall into this trap with C++, partly because of the way we have been educated in C++, the way that books love to talk about widgets, that everything is a class. We create a class for the async file writer because that is our default position. And we think of classes almost as programs. They are effectively self-contained systems with their own state, with their own semantics, with their own little world that they live in. When in reality, it is quite a lot simpler than that. And in this case, for example, the code arguably is also a lot less readable in the case of the async file writer class, because of all that boilerplate, which really doesn't necessarily add anything. And in fact, this is from real code. When looking at that code and refactoring it, it turned out none of that semantics was ever used. So it was pointless. So this is sort of, if anything, I think this is the kind of the essence of it. Think about C++ is an incredibly powerful language, but the main focus of C++, or the part of the really big focus of it, is of course to think about types, but not everything in your code is a type. So resist the urge to make it a class or a type. Ask yourself, could it be something else? And there's also benefits to that, not just for simplicity, in this case, not having to write so much, but also for the ability for someone to understand the code as they call it, as they are looking at the code where it's being used, the locality of it. And I'll get back to that in a moment. But C++ has some very powerful tools to allow us to build better, I would say better than C in many cases, interfaces, and to make more readable code because it has types. So for example, some of the power tools that we like to use in our code base, I think these are probably some of the most used features that are C++ features. Lambdas are great. So Lambda functions, incredibly powerful. They are, in my opinion, they beat macros any day. So because you can debug them, right? I can step into a Lambda function. I can create it right there and then inside of my other function. I can capture what is needed for it to be able to operate on state inside of the function. It improves locality because I can see right there. It's not a function outside of where I'm calling it. It doesn't have to be in a different translation unit. It's not in a different header file. I'm using it right here. If I need to move it out because others will use it, then so be it. But to start with, I will keep it right there. I can step into it. As you know, you can't do that with a macro. It can improve performance if you're using it with templates. So if you're really taking it to use it properly with C++, because the compiler is able to inline much more efficiently. It sees exactly what your intent is. It sees that function right there, and it can inline the whole thing. So for example, one of the many algorithms in the standard library that iterate over data, iterate over a container, and perform operations on it, they take predicates. If you pass in as a predicate a lambda, the compiler can pretty much unroll the whole thing in most of the cases. But it is important to understand how lambdas work in C++. It is important to understand how captures work, how they are being treated, when they are being allocated. Sometimes if they're very big, they need to be allocated, and all the different variations of how you do a capture, whether you are capturing this, or whether you're capturing just some variables, whether you're capturing by value or by reference, all of those things, it needs to be understood. Lambdas are powerful, but do understand them. And as a word of warning, at least with the latest Visual Studio 2019 compiler, there is an issue between debug and release in using lambdas and captures, which I have noticed, and it has perfectly rational behavior, but it can catch you out. So make sure that when you are using things like lambdas, which especially when it comes to the heavy inlining that the compiler will do in release mode, do test with release. Make sure that it does what you think it should do. Const expression is another fantastic tool, I think, from C++. Again, beats ifdefs hands down. It can improve performance because the compiler might decide that something, a function, for example, is actually compile time implementable. There are hash functions that you can implement like this, for example. However, keep in mind, it improves runtime performance, but not compile time performance. Compile time, the same goes with lambdas and everything else in template and C++ land. Compile time performance is not going down because runtime performance is going down. This is rather going up. This is an issue. It's a big issue with C++, in fact, because sometimes it does get forgotten that many of these features are heavily reliant on the compiler doing work, which means the compiler will take longer time. So make sure you keep an eye on it. If anyone knows of a good tool to measure the impact of piece of code on the compile time, I know there are some attempts out there to create that. But if you can narrow it down, and there is a tool that gives you the number of milliseconds a particular template instantiation added to your build, that would be incredibly useful. I haven't found one that really works yet, but I will be delighted the day I find one. Other than that, standard library has an enormous amount of powerful and fast implementations. There is no doubt about it. And I'm just going to call out some of the most useful ones in our code base. Unordered map, it's very fast. If you only use map, don't use unordered map. It's very quick. Uses a hash map implementation. Most of the time for your initial run, when you need a map, it will be fast enough until you measure it, and you might find that you need something faster. But don't just jump on writing one yourself. Standard unordered map is quick. Standard function is incredibly versatile. It allows you to create interfaces, APIs, which are much richer than what you would get with just using either virtual functions or traditional C function pointers. And it's a very good way of designing service-oriented APIs. And there are plenty others as well, but these are just the top sort of few that I think, in particular in our code base, that we find scattered around as being frequently used and that have some real low-level benefits that you can really take advantage of without having to dive in and become a C++ standards expert. So just to sort of summarize some of the mistakes to this point, we have done that a lot. Everything is a class approach, and again, I think it's a slightly sort of a disease that permeates a lot of C++ code, and it's just a habit. You start by writing my class, and then you think about what it's going to do. But do keep in mind that classes describe types, namespaces, or naming conventions in C, group functionality, and very often, in fact, I'd argue probably in most cases, what you are writing is about functionality, not about types. So keep that in mind and just use it as a guiding principle when you write your code. To that earlier example, the async file writer class does not need to be a class. It's not class, it's functionality, and it can be grouped under a namespace, and you're done. One of the other problems with virtual inheritance and some of the abstraction that we tend to do, some of the obfuscation that we tend to apply when we write things as classes, we tend to sort of wrap up and hide away state and the inner workings of our class, and we sort of surface it in a small function at the beginning, in the public part of the class, with an enormous tip of the iceberg effect, with an enormous amount of code happening under the hood. And anything that is manifest only at runtime is incredibly hard to reason about. Virtual inheritance is probably the best example of that. You have a interface that you're passing around. Maybe you're doing some sort of dependency injection type approaches, very popular in other types of languages like C#, for example, but you might take that sort of approach in your code. As a developer coming in and looking at your code, I have absolutely no idea which one of these interfaces maps to what implementation, because that's being decided by some code running somewhere else at some other time. It makes it incredibly hard to reason about your code, and it makes it incredibly easy to make really, really bad mistakes. So not talking about virtual inheritance as, oh, it's a slow thing, that old chestnut, I think, thankfully, we have put behind us. This is purely about, can I look at my code? Can I drop into the code at a location, locally, and get an understanding of what's going on? And the locality bit is really key. I mean, I want you to keep that in mind. You've stepped away from your code, or you've brought someone new onto the team, and they're dropping into your code, and they have a visibility of maybe 80 lines of code right there in front of them on the screen. And if those few lines that they're looking at where there is a bug or something is happening that they don't understand, if the paths into that point of code are hundreds and they are distributed in files many levels away, and they are dependent on decisions made at runtime, then that is going to be a very difficult task to decipher. And the result will most often be that people will work around it. You'll find a problem with code that has had many contributors to it. You'll find a problem with it, especially if you don't use code reviews. You'll find code where people have worked around the intent of the code because it was just too hard to understand what the intent of the code was. It was too hard to see where something actually had a cause and effect for what you're looking at. So be very aware of that. And as tempting as it is, I mean, the example here of virtual inheritance for cross-platform functionality sounds crazy, but I have seen it in code, not in our code, thankfully, but I have seen it in code. And it's sort of almost understandable as a glib reaction, because everything is a class. It's such a common thing to think about it, but it's not a good idea. Because again, locality of code. It is all about locality of code. If I can look at the code and I can understand there and then what your intent is, then that is a win, and it will really help you as you develop your code further. And we are spending a lot of time in our code base to improve locality of code. Yeah, hard-coded constant is a thing. You know, I think hard-coded constants are a bit like go-tos. You either love them or hate them. And a lot of people in particular, and myself, I must admit, I don't like it when I read some code and there's a number in there, 101. What does it mean? But sometimes you just want to have a number there, and you don't want to put that number in a constant or a define at the top of the file, because now I have to go to the top of the file. Even with IntelliSense, you know, it's fine, but I go into the top of the file and I see all these numbers. Who's using them? Why are they here? So what I do, my tip, is on the line, let's say before this function call where I need to pass in 101, I do a simple const expression, either using auto or the type itself. And then let's say I call it k, the number of iterations, equals 101. And then on the line below, at the function call site, I slot in the number of iterations constant, that name that I've just created. And it's just there. And you could say, well, that's slightly redundant, but I've kind of documented it now. I've made it a thing. It's right there, but I made it a thing. Now I could arguably also put in a line of comment there, but by doing it this way, it also means that I've sort of said, if this at one point needs to become used somewhere else, you'll move it up. It has already got a name now, so you can move it to the top of the file. It can be a const expression there, and it's all fine. It's just a good practice, and you might have other versions of it, but the point is, make sure that you put something in there, make it local, make it possible to reason, think about your future self. So the rule here is sort of a variant of the old rule of optimization, which is don't do it. It's don't abstract yet. Abstract when you know that you can abstract. You know, there's a classic thing that if you have written a piece of code and you think is general reusable code, it's only general and reusable when you have used it 3 times in 3 different scenarios. Before you've done that, it is probably not reusable. And it's the same idea with abstraction. Getting better at doing C++, and we encourage this at Polystream for all of our engineers, is actually a lot about learning other languages if you can. And so knowing your craft, because C, pure C, C99, for example, has some really cool things in it that I really recommend. And in fact, if you want to see some good C code, there's plenty of it out there. Obviously, you can look at the Linux kernel, has a lot of good C code. I personally really like Andreas Weisflog, his Sokol, S-O-K-O-L library. It's a cross-platform graphics library. It's a single header type library, and it's written in pure C. It's very good for looking at, I would call, good best practice C code. Do that, look at some code like that, look at Rust. I must say I've never fallen in love with Rust. I like it, but it's quite a sharp edged language to use. Zig is another language coming up, which I personally have a lot of love for. Ways of thinking about what the language should do and shouldn't do for you with hundreds of years of experience, as opposed to, quite frankly, C and C++, which of course have just piled on top of what we did 50 years ago, or whenever we first started thinking about it. Python and languages like that, they are really important to understand and to learn, because with a language like Python, you can express your intent without having to struggle too much. You don't have to fight the language to express what you want to do. And that is a really valuable and important lesson. So what I personally like to do is I like to go out and look at these languages. I have, if I can, I have a little, Hello World pet project, whatever, in one of them. And then I go back to C++, and then I ask myself, what can I learn? What can I bring back? Because I don't want to get too stuck into just the C++ way of doing it, because as I think and I hope I've showed a little bit in this presentation so far, it is easy to get stuck in the rut and to do things the way you think they should be done, but actually they are inefficient and they're not well thought through. It really comes down to always think about what you do. And always measure things, right? Performance, whether using, the reason why I can say I know standard unordered map is quick is not just because I've read it on the internet, it's because I've taken the time to write something to test it. There's plenty of tests out there. You could say, well, that's a bit pointless, but actually measure things and learning how to measure things, how to trash a cache is a good thing to do. So almost regardless of what kind of code you write, I would recommend taking a detour and trying that out. Reread your code often, use peer reviews. So we started using GitHub pull requests. That mechanism is really good. We use GitHub for all of our code, both public and private. And pull requests are good. People have comments, and some people love and hate the way that it presents the differences. And of course, there's Git behind it. Not everyone likes Git. Point is, though, that you do that, you have a firewall. I push something and I want to integrate it into the development mainline, someone else has to look at it. And this is actually one of, I find, the best ways of avoiding the problem of people working around the code, because you get someone to review it who wrote the original code, or at least is very familiar with it. And they will look at what you do and they'll ask, why are you doing this? You should be doing that because X, Y, and Z. So if you're not doing peer reviews of code, if you think it's a waste of time, it really isn't. It is super useful, and it will make you a better programmer. That is just a good thing. Do make sure you understand your platform. I mean, some people make that a life mission to understand every bit and transistor of the platforms they're working on. You don't have to do that, but you do need to understand your platform. Understand what is costly and what is not costly on Windows, or if you're running, if you're building for consoles or whatever it is. Even if you are writing code in existing engines like Unreal or Unity, do take the time to understand what costs and why it costs. And because this is important, and it's interesting. I've been programming for a very long time, very long time. And I find it amusing and slightly disturbing that there are still presentations out there today, new presentations, that talk about the difference between structs of arrays and arrays of structs. If you don't know what it is, Google it. Because you should almost think that today everyone should be aware of the performance penalties and cache lines and what there might be going on under the hood. We don't all have to be experts, but it is important to understand it, because everything costs somewhere, someone pays. And back to our earlier comments about things like compile time, optimizations, templates, etc., nothing is for free. And if your super smart code means that your build times have increased by 10 minutes, that's not a good thing. And vice versa, if you're using a new library or importing a new function, for example, you might have decided, no, I'm going to write my own map implementation because I know how to write a fast one. You might actually find that you wasted your time doing so. So do understand what you do understand what you're running on. It will also make you a more empathetic programmer. And I think that is a useful thing. So both for the language and for the OS and for all the tools you use, do understand them. One last thing I want to call out, and that's to do with performance, and it's sort of to do with I guess it's a philosophy of how you treat performance, really. Explicit resource management. So it is simply not good practice to hide away resource management. Again, something that I think is a little bit endemic of C++, object-oriented design, is that you hide away things, you make it really convenient. I can call this function and it will do all magic stuff for me. And that's wonderful. But as anyone who's listening to this, who's had to track down memory fragmentation issues in code that allocates tiny strings or tiny buffers and frees them again and just fragments the hell out of everything on a console, as anyone who's done that and pained through that will know, hiding away resource management is not a good idea. I will actually go as far as to say that the best approach, and this is something, for example, that Zig, the language, very much advocates, is make memory allocation super explicit in your API that you're calling. So if you think back at the async file writer, for example, which will have to do some sort of memory allocation under the hood, pass in an allocator. Say, here's the allocator you're going to use. Standard allocator, some of you will be familiar with, is a template allocator. Yes, you can use that. Again, you are locking yourself into type. There are also some issues around how easy it is to adapt it for instances, to have different instances of the allocator, because it's a template. They get created internally by the caller. There are pros and cons. It's not a terrible solution. I would definitely recommend looking into it and understanding it and see if you can take advantage of standard allocator. But a really simple place to start is you create an interface or a struct with function pointers, doesn't really matter, whichever you're more comfortable with, and that's your allocator. Now, it will make me have to think a bit more. I will have to say, create resource, or whatever call it is I'm making, pass an allocator. And I have to ask myself, which allocator should I pass in? Well, if create resource, if the author of that wrote a good API, they will have said, this will need an allocator. They can use a general allocator, but optimally, you should use something that is a small object allocator, for example, or fixed size allocator, or whatever it might be. And I can tune that. Or I can pass in an allocator that is tagged specifically with this piece of code, with this domain that I'm working on, so that later on, when we're fragmenting stuff, we can look at the map coming out of the allocator and we can see, aha, all of that fragmentation came from that part of the code because that's where it's tagged. Super useful. And it makes you think about resource management. And I mean, it extends, not just memory. Memory is an obvious one, but threads is another one. I have seen horrible examples of implementations, and I probably made some of those mistakes myself, if I'm going to be brutally honest, where a class functionality actually creates threads under the hood. It will, to make, let's say you have a class that does fetches something from a website or does some sort of HTTP call or whatever it might be. And it helpfully creates a thread so that you can call it and you don't have to block on it. That is a bad idea. Thread management, just like memory, is something that needs to be managed centrally by the application. If you have going to have any hope of making your application robust and efficient, you need to manage it centrally. So don't put the thread management inside of behind a firewall, behind your API. Make sure that it is open. Make your APIs non-blocking. In other words, make it the caller's responsibility to deal with the threads. If your function is non-blocking, and I appreciate that can't always be done, it's not always trivial, but if it can be non-blocking, and spend some time thinking about it, then the caller will decide, do I start a thread to do this in a asynchronous way, or is it okay that I just poll it in a while loop or whatever it might be? Make it their responsibility, because then they have the choice and they can control performance in a way that they can't if you just magically do it for them. And take that further. Prefer callbacks for platform-specific resource usage. Instead of if-defing platform-specific usage, for example, or even using standard library to open files, make that something that you are passing in as a service provider, because even if it turns out to be that most of the time you write a stub that uses standard F-stream, you will at one point, and I'm not saying you should think too far ahead of it, but it encourages a very, very healthy and good way of thinking about resource management. Right, that is all that I wanted to say about these things. I hope it's been useful in some way. I thank you for listening if you have. In these COVID days, doing a presentation to an empty room, looking at a camera is always a challenge, but hey, we learn and we live. So thank you for any feedback you might give. I'm contactable. I'm sure through Develop, they will provide contact details for the speakers. My details on Twitter are there. You can DM me. We have also Polystream's GitHub repos. Some of them are public. You can have a look, take a look at our website, and happy coding. Thank you.